Now we're discussing the strain-based approach to fatigue, and we've already established a relation, the Coffin-Manson relation, that essentially delivers us the number of cycles to failure given the strain amplitude, the total strain amplitude. We do, however, immediately recognize that we have certain limitations, and these limitations are important limitations, and that we had previously addressed them in the context of stress-based approach to fatigue. And let us summarize once again and highlight their importance. One, first of all, we assumed that we had zero mean strain and essentially therefore zero mean stress. Now, in reality, we do not necessarily have zero mean strain, and therefore this has to be accounted for. So we need to account for mean stress, or alternatively mean strain effect. Two, well, we assume that we have only a single strain that is varying, which is the normal strain. Of course, we can have multiple strains varying at the same time because we have multi-axial loading. So that's certainly something that needs to be addressed. Three, we assume that the amplitude of the strain does not change. In general, we can have variable amplitude loading, which certainly needs to be also addressed. And finally, and very, very importantly, we need to look at the effect of notches. So far we assume that there is, implicitly assume that there is no stress concentration. And in fact, this is exactly where the strength of strain-based fatigue lies. Because it turns out that first of all, when we have significant plasticity, then we've already observed that the number of cycles to failure is low, and significant plasticity is naturally induced in the presence of stress concentrations. And since strain-based fatigue is naturally taking into account plastic deformations, we can imagine that it is going to function better in such scenarios. And therefore, strain-based approach is more suitable. So significant plasticity associated with, or if, let's say, KT is large enough, is naturally addressed by the strain-based approach. So notch specimens is actually a strength of the stress-based, strain-based fatigue approach. Now, we are presently not going to address these generalizations. We've already discussed them in detail in the case of stress-based approach to fatigue. So the approaches do have differences in the case of stress and strain-based let's say, formulations of fatigue. Nevertheless, they are, since we've discussed one in detail, we can safely, let's say, omit the other one because we're in a position where we can, on our own, go into the reference book and study the relevant generalizations with relative ease, with the understanding of the generalizations that we've discussed in detail in the stress-based case. So let us proceed, therefore, and demonstrate the strain-based approach as we've discussed this so far in the context of a simple example. And this is going to be an example where we take, again, RQC 100 steel. Okay. Remember that just like in all the previous cases, we will collect the data from the tables that are provided in our book. And what is given to us is that the stress amplitude is prescribed, 501.2 MPa. The mean stress is equal to 0. And so that's what we've assumed so far. And KT is equal to 1. In other words, we are dealing with unnotched specimens. And finally, we're looking at uniaxial loading. There is no other stress. So it's exactly the approach that we are discussing, and the amplitude does not change. So it fits these limitations. And that's what the Coffin-Manson equation in its original form stands for, just like the Basquin equation in the case of stress-based fatigue. Now, and the question is simple. What is the number of cycles to failure? Okay, that's what we would like to find out. And we want to do this through the strain-based approach to fatigue. If it were a stress-based approach, I already am given the stress amplitude, and I can immediately use, let's say, the Basquin equation, right? But that's not what we want to do. We want to use the strain-based approach. So it's clear that in step number 1, I need to somehow build a relation between the stress amplitude and the strain amplitude so that I can employ the Coffin-Manson relation. So that is realized by, in the solution, in the first step, by invoking the relation between the strain amplitude and the stress amplitude as modeled through the Ramberg-Osgood type relation, which says that the total strain has a elastic part plus a plastic part. And these parts I can easily remember through the Ramberg-Osgood formulation. So presently we are given everything. In particular, sigma A is given as 501.2. We can look up in the tables and find that E is 200 MPa, H prime is equal to 903 MPa, and N prime is close to its usual range, slightly smaller perhaps, 0.0905. Okay, so this being the these being the material parameters and sigma A being given as 501.2 MPa from the cyclic stress strain curve of model through the Ramberg-Osgood relation, we can go ahead and directly determine epsilon A, which is equal to, let's write that in red, epsilon A is equal to 4 times 10 to the 3. Okay, so this is, let's say, Ramberg-Osgood type relation. Now, having that result at hand allows us to continue into the second step. And now that we have the total strain amplitude, we can immediately predict number of cycles to failure based on the Coffin-Manson relation. The Coffin-Manson equation says that, well, again, this is not something I necessarily need to memorize at all. Well, I remember that epsilon A, again, has an elastic part, which is conveniently written as sigma f prime over E 2nf to the power b based on the Basquin equation form. And the presence of the Young's modulus reminds me that this part has to do with the alternating elastic strain, and the remaining part is through the alternating plastic strain. And it has a form that is very similar again to the Basquin form, but this time instead of sigma prime f, we have epsilon prime f, and the exponent is not b, but something else, c. So in this case, again, well, sigma f prime is provided. It is 938 MPa. E is provided 200 MPa already. B we can find out it is minus 0.0648. C likewise we find from the tables to be minus 0.704. And finally, epsilon prime f is 1.38. And here, the only unknown is NF because epsilon A is known from the previous step. And therefore, we can go ahead and determine number of cycles to failure, which comes out to be 8,124 cycles. Okay. So this is not a very small number. It is also not very large. So we are curious as to whether this is more towards high or more towards low cycle fatigue. And this is where the transition fatigue life becomes convenient to make use of. So first of all, notice that as soon as I know what NF is, I can actually predict the elastic and plastic contributions to fatigue and to the overall strain, and compare essentially what they are. Well, I have these relations which try to attempt the same thing, and here I know that this is epsilon EA, and therefore I know that I can go ahead and evaluate because sigma A is already given. I could have done that before. Epsilon EA here is about 2.51 times 10 to the minus 3, whereas the second part is associated with the plastic strain, and that, if you evaluate it explicitly, is 1.49 times 10 to the minus 3. Okay, so I noticed that the elastic strain is a little bit more than the plastic strain, so I suspect that this number is closer perhaps to the high cycle regime. But let's see if the transition fatigue life actually supports that observation. So now again, the transition fatigue life is not something I need to memorize. And I just remember that in order to invoke the idea of the transition fatigue life, I need to say that the elastic and plastic portions of the strains, as they contribute to the number of cycles to failure, they should be set to an equal value. That's where the two lines that we have for these two individual contributions cross. Okay, so this is in the life expression, the elastic portion, and that is epsilon EA, which is sigma F prime over E, to number of cycles to failure is equal to the plastic portion, C, that's the plastic portion, and the transition life is where they are equal. So we can go ahead and solve for NT from that equation. So as soon as I understand the individual contributions to the Kaufman-Manson relation, I should be able to extract this information with an understanding of what the transition fatigue life stands for. So here, notice that we have everything we need to know. So sigma F prime E B, EF prime and C are all known. So NT is the only thing that we need to extract from this equation, and therefore we can solve for it, and we can find that NT is equal to, in this case, 3,640 cycles. So notice NT or NF is quite large compared to NT. So this supports our earlier observation that we are in a regime that should certainly, of course, since epsilon EA is larger than epsilon PA and F larger than NT is implied because equality of the two strain contributions occurs at NT. So we are towards the high cycle regime. But we cannot really say that we are in the high cycle in the classical sense where we have little or no plasticity, because the plastic strains, yes, they are smaller compared to the elastic ones, but still there is significant plasticity. So 8,000 is a relatively large number of cycles, at least in relation to NT, but still it's not large enough. So this is where, again, perhaps the strain-based approach to fatigue has its own advantage because it's able to take into account those plastic strains in the formulation of the fatigue relation. All right. Now, having said all of this, let us make a peculiar observation. And I will draw a let's say a line here to make that observation, and might be confusing at first, but let's say remark, and the remark is the following. Well, we discussed at various stages the elastic and plastic contributions to the overall strain, and when I look at the Ramberg-Osgood relation, this is the elastic contribution to the strain. Okay, So in other words, E times the elastic contribution to the strain amplitude is equal to the stress amplitude. Now, at the same time, we also said that the total elastic strain is associated with the elastic contribution to life, okay, or the life elastic strain relation through this portion of the total strain, okay, or this portion of the total strain life relation is associated implicitly with the elastic portion of the strain amplitude. So when I multiply this likewise with E, we get, and let me put an exclamation mark there, sigma f prime 2nf to the power b, right? If on a log-log scale epsilon EA versus NF is linear, then stress amplitude, if it is supposed to be E times epsilon A, is also on a log-log scale linear with respect to NF. And we call those constants sigma f prime and b, which may or may not be equal to those that appear in the high cycle regime for Basque-Cohen equation. It turns out in this case, by the way, that these constants are exactly the same constants that you would find in the tables for high cycle fatigue for Basque-Cohen equation. Okay, so that's a side remark. Now, therefore, from this relation directly, I can solve for NF. Why? Because I already know sigma f prime, and I know the value of b, and I am, from the outset, given the value of sigma a. So actually, without going all the trouble into first determining epsilon a and then solving for Coffin-Manson relation, I can determine NF. And by the way, notice that in order to solve this equation for number of cycles to failure, it's not something that I can easily do analytically because it's a nonlinear relation in terms of NF versus epsilon a. So this is probably somewhere where I need a numerical solution. Just like if epsilon a was given and I wanted to find the corresponding stress amplitude from the Ramberg-Osgood relation. So now, therefore, I don't have to go into any of that trouble, and I could directly find the value of the number of cycles to failure. And it would be, let's indicate it here, it would be, let's call it NF, and 7,933 cycles. Now, I'm going to call that NFE, the superscript E, indicating that it has to do with the elastic relation, elastic portion of Ramberg-Osgood, elastic portion of Coffin-Manson. Now, I got a result that's different from what we got over here. This is our main result that we are comparing against. Okay, well, we could have done something similar for the plastic portions. So let's draw a line here. And what we could have done is, we could have said, well, all right, the plastic portion of the strain amplitude is simultaneously, first of all, from the Ramberg-Osgood relation, sigma a over h prime, 1 over n prime. But on the other hand, when I look at the strain-life relation, I see that this portion is also associated with this plastic strain amplitude, so it's equal to epsilon prime f, 2nf to the power c. And now what you can do is you can look at this relation, and actually you can now extract a stress versus life relation that looks different from this one because it's based on not the elastic strain but the plastic strain amplitude. So if I simplify this relation, keep sigma a on the left, okay, and then I will raise each side to a power of n prime, so it's epsilon prime f to nf to the power c, and then everything to a power of n prime, and then multiply through h prime. I now have a stress life relation. Let me put an exclamation mark here, right? One side of the exclamation mark has to do with Ramberg-Osgood. The other side of that exclamation mark has to do with the Coffin-Manson relation. Okay, so here I got a relation for stress amplitude versus life that we hadn't seen before. Okay, and does it fit into the Basque-Cohen form? Notice that it does, because there is life raised to some eventual exponent, and there is a coefficient in front of it. It's just that it's expressed in a complicated way. But ultimately, this is also on a log-log scale, predicting a linear relation between stress amplitude and life. So it's just another Basque form. It's just expressed in a slightly different fashion. Okay, so here I also know the value of h prime. I know the value of epsilon prime f, c, and n prime are given. And I can go ahead, therefore, solve for the number of cycles to failure, because sigma A is also given from the outset. So I don't have to go through this trouble. Given sigma A and all the material constants, I can use this equation if you like. And the result is NF equals 8,141 cycles. Okay. Now let me call this NFP, because it's a stress-based life prediction based on the plastic contributions to these two relations. Okay. Now the question is, well, what is going on? So certainly this value is very close to this. This value is even closer to that, but they're not equal. Whereas we're using the same constants. Concepts are total strain is elastic plus plastic, so everything should be consistent with each other. Now the trick is actually, or the reason why we have a discrepancy between this result and these results is the following. Now notice that when I'm invoking these parts of the argument, so let's put them in blue, these exclamation marks are important because we're saying that, well, the elastic portion is either this or that, or either this or that. In other words, the left and right hand sides of these equations have to be consistent with each other, which suggests that the constants that we provide here are somehow such that that consistency holds. If I give you a number of cycles, if I give you a stress amplitude that is associated with failure based on the stress amplitude, let's say I give you 501 and 8,124, you plug them in here, it has to hold. It doesn't, it won't, because for it to hold, NF should be not that, but this, okay? And that's because, or in this case, NF should be not this, not that, but this. And the reason is because when you look here, you see actually here 4 constants, right? So let's make a note of that with red. So here we have 4 constants, which are sigma f prime, b, epsilon prime f, and c. Here, in this model, we have 2 constants. But really, additionally, we need to say that this actually is equal to that. And let's say this is equal to that. That actually places 2 additional constraints such that I don't have overall 6 constants. Okay, so let's put an exclamation mark here as well. So it's a big question mark. I seem to have 6 constants, but really I don't have 6 constants because I have 2 constraints which say that the corresponding contributions to these equations, this one and that one and that one and that one, they have to be the same. So really I have less. I have 4 constants that I should be working with. But in practice, what people do is they, to maintain some flexibility in fitting the data, they regard all these 6 as independent constants. So therefore, you end up sacrificing from the theoretical equality between these and these contributions, and therefore these exclamation marks do not strictly hold, and as a result, the results you obtain from those equalities, in other words, these 2 predictions, do not match what you predict from the Coffin-Manson equation directly. So having said all of this and clarified the source of this discrepancy, let me tell you that the suggested practice is to go for the relation between total strain and number of cycles to failure. In other words, when you look at the Coffin-Manson relation, yes, the interpretation is elastic plus plastic, but we really are ultimately interested from a modeling point of view, total strain versus life relation. And so we do not do this decomposition, because if we do, we can end up with slightly different results. The data is fit in order to predict this well. And therefore, this is our prediction. This is the best according to our judgment with this model. So our reference result is going to be this one and neither of those. Although, again, there is a discrepancy due to this choice in the data fit by regarding all these constants as being independent. But notice that the discrepancy is not always large. Sometimes it can be large, sometimes it can be very small. And in this case, actually, it is rather small. Again, our reference is this value. So, and therefore, the way we have proceeded demonstrates the intended way of proceeding with the application of the Coffin-Manson equation.